Namaste, students, and welcome. Today, we're going to explore something you probably see every single day, right in your own kitchen. Let's begin. Have you ever wondered about this? Why does your puri or your sabji cook so much faster when you increase the flame on the stove? Well, the answer seems obvious, but the chemistry behind it is actually very, very interesting.
And that answer is our topic for today, the temperature dependence of the rate of a reaction. Now, understanding this isn't just about passing your exams. No, this concept is critical for running large chemical plants, for developing new medicines, and even for understanding the thousands of reactions happening inside our own bodies.
Okay, so we all know that a higher temperature means a faster reaction. That's clear. But the really interesting question is, how much faster? The answer might surprise you. You see, for many, many chemical reactions, there's a general rule of thumb. For every 10 degrees Celsius increase in temperature, just 10 degrees, the reaction rate often doubles, or in some cases even triples. Just imagine that for a moment. A small 10-degree change can make a reaction 2 or 3 times faster.
Now, this is a very important point, so please pay attention. A lot of students get confused here. They think that changing the temperature is similar to, say, changing the concentration of the reactants. But that is absolutely not correct. You see, changing the concentration usually has a proportional or a linear effect, but the effect of temperature, that is exponential. It is much, much more powerful.
So why? Why is temperature so powerful? To really understand the why behind this, we need to think about a central idea in chemical kinetics. Let's call it the energy hill. You see, for a reaction to take place, the reactant molecules must collide with a certain minimum amount of energy. And this minimum energy has a name. We call it the activation energy, written as EA. A very good way to visualize this is to imagine an energy hill. For the reaction to go forward, the molecules literally have to climb over this hill. So let's think about what happens at a low temperature. At a low temperature, most of the molecules are moving around quite slowly. They collide, yes, but they don't have enough energy to get to the top of that energy hill. They might try, but they just roll back down. Only a very, very small number of molecules, the most energetic ones, are able to make it across. But what happens when we increase the temperature? Now, this is the most crucial part. The height of the hill, that is, the activation energy, it doesn't change at all. What changes is the energy of the molecules themselves. At a higher temperature, a much larger fraction of the molecules now have enough energy to successfully climb over that very same hill. To make this concept crystal clear in your mind, which is very important for your exams, let's use a simple analogy. Just for a moment, forget about molecules. Instead, I want you to picture a group of runners who are trying to climb over a very high wall. So imagine this. There's a huge crowd of runners. These runners represent our reactant molecules, and they're all running at different speeds. Some are fast, some are slow. And right in front of them is a big, high wall. This wall, this is like our activation energy barrier. To complete the reaction, a runner has to be running fast enough to be able to jump over this wall. Now, let's picture the low temperature scenario. In this case, most of the runners are just jogging along slowly. They're not very energetic. So only a handful of them, the fastest sprinters in the group, have enough speed to clear the wall. The total number of successful jumpers is very, very low. Okay, now let's imagine the high temperature scenario. We've given everyone an energy drink. The whole group of runners is now much more energetic. They're all running much faster. Now listen carefully. The wall is still the same height, but because the runners are faster, many, many more of them can now easily jump over it. So the number of successful jumpers increases dramatically. So we have this idea of an energy hill and our runners jumping over a wall, but where do we actually see this in the real world? Well, this single concept explains everything from why your bicycle rusts to how massive chemical plants avoid dangerous explosions. Let's take a simple everyday example, the rusting of iron. At about 4 degrees Celsius, maybe like inside a refrigerator, it might take weeks for you to notice any rust. At normal room temperature, say 25 degrees, it only takes a few days. But if you were to heat that piece of iron to 60 degrees, you would see significant rusting in just a few hours. This is that exponential effect, visible right before your eyes. Now, this exponential effect can also be very dangerous. In large chemical factories, some reactions actually produce their own heat. This can create a dangerous cycle. First, the reaction releases heat, which increases the temperature. This higher temperature then makes the reaction go much, much faster. This faster reaction then releases even more heat, even more quickly. This dangerous feedback loop is called a thermal runaway, and it can lead to explosions. Understanding temperature dependence is absolutely critical to prevent this.
So if there is one thing you must take away from this explainer, it is this. You might think a 10-degree rise in temperature is a small, insignificant change, but in the world of chemical kinetics, it is a huge change. Its effect is not linear, it is exponential. This is the single most important idea you must remember.
All right, we have covered quite a bit of ground. So let's quickly summarize the most important points from this topic that will help you in your exams. If you can just hold on to 3 key ideas, let them be these. First, remember that the effective temperature is exponential. A small temperature change causes a big change in the reaction rate. Second, hold on to that analogy of climbing the energy hill. A higher temperature simply gives more molecules the energy they need to cross that barrier. And third, keep a real-world example in mind, like cooking food or the rusting of iron. So, I'll leave you with a final thought. The next time you are in the kitchen and you turn up the heat to cook your food faster, I want you to try and picture it. Imagine all those millions of molecules gaining that extra energy, getting ready to make that jump, and climbing over the activation energy hill. I hope this was helpful. Thank you.